Hello, welcome to The Nerd Show. I'm your host, The Nerd. Today, we've got a little special guest here. This box. Boxes tend to have stuff in them, so we could just open it up and see what it is. But first, got something written on it here. It says video topic string, and that says two things. One, that whatever's in this box is the video topic, and two, that it's a string. And I don't mean a physical thread. No, I'm talking about a string in terms of computer science, which is a sequence of characters or text. Now this box right here is a little bit like how variables work in all sorts of programming languages. You define a variable by giving it a type and a name, as well as a value. But not every programming language has you set its type. Take, for example, Python or JavaScript. These languages are typeless, as in you can give a variable without setting its type. But no matter the language, a variable is always used to store data in a program. But what if you want to store it outside the program? Computers at this moment in time think in binary. All their data and all their programs are run in series of ones and zeros, ons and offs. And when we're talking about data, these bits are clumped together in groups of 8 called bytes. And these bytes can be interpreted into all sorts of data: text, numbers, images, audio. And when they're stored in your computer in the form of files, they're generally given an extension: .txt, .exe, .png, .mp3. This tells the operating system of your machine exactly how it should interpret the bytes in the file. And when it comes to programs, sometimes there just isn't one specific file type that you can use. If you want to store a bunch of numbers, well, you could just write it in text, but as I've learned the hard way, that doesn't really help. It makes things messy and clunky. The reason we give all our variables a name is so that we, the programmers, can keep track of it. The computer doesn't care if you name a variable Poop Fart McGee. Is that really what I wrote? It's only going to care if you're using the correct variable name when accessing it. And so there's a file format that takes this sort of approach called JSON, or JavaScript Object Notation. JavaScript Object Notation is a file format that's, well, obviously built off of JavaScript. It's very useful for storing primitive data in really anything. And because it's built off of JavaScript, it uses JavaScript's typeless philosophy. Nothing that is stored in a JSON file is given an explicit type. Like how in JavaScript you write var variable name or let variable name instead of int variable name, string variable name, or std : open angle bracket std : string comma uint 8 underscore t closing angle bracket variable name. Another thing that JSON is built off of is the object. That is one big box to put little boxes into. This is syntactically represented by curly braces, and it's what a whole JSON file is surrounded by. Every time there are curly braces, you have encountered an object, and anything between those curly braces is a part of that object. There are little boxes with their names inside of a big box. And when you want to access any of these little boxes, you tell the big box, I want variable such and such. All the elements in a JSON file can be a string, a number, null or nothing, true or false, an object, or an array. And we've already talked about objects, but an array is also a list of elements, except it's only the values of elements. Instead of telling an array that you want the variable named such and such, you tell it, I want the variable numbered this. And what you're giving the list is an index. When you say, I want the element at index 0, you're telling it, I want the first element that you have. And while this typelessness really makes it easy for humans to read JSON, it's kind of a guessing game for the computer whenever they're parsing a JSON file. JSON stores everything in the form of text, as in that number 122 isn't stored as the number 122, it's stored as the characters 1, 2, 2. Because of this, JSON needs to be parsed in order to find out which elements are which and what their actual value is. If there are quotes surrounding a value, you know it's a string, but the computer has to find that out itself by looking at the text in whole. And this isn't a super big deal for JavaScript because JSON is built into JavaScript. It would be surprising if JSON didn't work in JavaScript. But when it comes to other languages, they need to know what type it is explicitly sometimes. Because of the way their memory works, they can't say, have an int go where a double needs to be. They need to know exactly what type they're getting and how they should store it. And some languages, even old ones like Java, have ambiguous types that you can use. But if you put an int in an ambiguous type, you still need to tell it to give you an int back to use it. Because Java isn't a scripting language. JavaScript is, but not Java. Java does sometimes just go on the fly, but not all languages go on the fly. They need to know explicitly what is where and where is what. They compile things into a program and run it. Thankfully, there's another option. If you want a data structure that allows you to store primitive types but doesn't have the same hassles that JSON does, I would opt for NBT. NBT stands for named binary tags, and it works exactly how it's named. Every element in an NBT file is a tag, and they're given a name and stored in binary rather than text like JSON stores. NBT was created by Marcus Notch Person after I sold him Minecraft, likely to store worlds at small file sizes with ambiguous file types. One of the main things that makes NBT different from JSON is the fact that everything is typed. There are byte tags, short tags, int tags, long tags, float tags, double tags, list tags, compound tags, byte, int, and long array tags, and so on. It seems like there are a lot, but really these are all primitive types, with two exceptions: compounds and lists. A compound tag is like an object in JSON. It's one element that stores a bunch of named elements within it. A list tag is kind of like an array, as it stores the data of a bunch of tags. And like a JSON file, an NBT file always starts with a compound tag, and every tag has a header, and that header goes something like this. 1 byte tells you what the ID of the tag is. This ID is used to tell you what tag it is. In this case, it's a 0x0a, or 10 in decimal. That tells you it's a compound tag. Following the compound tag is data that tells you what the name of the tag is. And there are two ways to store strings in data. One of those is a length-based string, where the data tells you the length of the string, and then you just read out that many characters in order to get the string. The other way is called a null terminating string, where you read an ambiguous amount of characters until you hit a specific character that tells you to stop. This character is 0x00, or null. NBT goes with the length-based string approach, and generally it can be faster than null terminating strings, because if you have read the data, you know where the string starts and where it stops, so you can just copy that into your string, instead of having to loop through a bunch of characters until you're supposed to stop. And so, NBT gives you 2 bytes to tell you how long the string is. This is an unsigned short, or an integer that can go from 0 to 65,535. And this means you can have names that long. Once you read the name length, you read that many characters, and that's when you hit the payload. The header is universal across all tags, but the payload is always unique to each tag. For example, let's start with a byte tag. A byte tag ID 0, after reading the name, will have a single byte stored for you to read. This byte doesn't always have to represent anything. It can represent an integer from -127 to +128, or it could represent a single character, or it could just be true or false. Whatever the case may be, it is a single byte and it's up for the programmer to interpret. The next tag after byte tag is a short tag, and that is 2 bytes of data. I already said how the name length is a short, and it's the same with the data of a short tag, but this time it's signed. That means it can be either positive or negative. This means that this number ranges from -32,000 to +32,000. Following that, we double the length again and we get an int. An int is 4 bytes long, ranging from -2.1 billion to +2.1 billion. Finally, we reach a long, which is the biggest integer type. This is an integer ranging from negative 9.2 quintillion to positive 9.2 quintillion. There are also floating point types. A float tag, which has a payload of 4 bytes, which is interpreted into a single precision floating point number. These numbers typically have a precision of about 7 decimal places. Following a float tag is a double tag, or a double precision floating point. This is 8 bytes and generally has a precision of about 17 digits. Going past these static length numbers, we have a byte array tag. This tag has 2 elements in its payload. The first is an integer that tells you how many bytes are stored in this array. After you read how many bytes there are, you read how many bytes there are. There are also int and long arrays. There aren't short arrays or float or double arrays, but there are int and long arrays. They have the same story, where they read an int telling them how many elements there are, and if it's an int tag, it'll read that many integers. If it's a long tag, it'll read that many longs. A string tag is sort of like a byte array tag, except instead of having an integer telling it how many characters to read, it has a unsigned short telling it how many characters to read. Again, going up to 65,000. After a string tag is a list tag, or a tag that can contain the payloads of any other tag. A list tag's payload is a little bit complicated. After reading the header, you read another single byte ID. This ID matches the IDs of all the tags, and it tells you what data is inside the list. A list must contain data of the same type. If you read the byte ID 1, then it must contain all bytes. There cannot be an int somewhere in there. Following this ID is an int telling you how many entries there are. Say if this number is 0x01 or byte, and this number is 0x00000005 or 5, that means there are 5 bytes to read. And although these are byte tags, you don't have to read their ID because you already know what their ID is, and you don't have to read their name because they don't need to have a name. You access them by their index in the array. If your list is of strings, then you read 2 elements per payload. You read the number of characters in the string and then the string. A list of a list can be tricky because the list has such a complicated payload. The final tag is the compound tag, the tag that has all the tags inside of it. After reading the header, the first thing you will read is another tag. This tag doesn't have a length. There is no set amount of tags inside of it. Instead, a compound tag is null terminated. When you read a tag, if the ID of that tag is 0, then you have reached the end of the compound tag. This 0 ID is the ID of an end tag. However, an end tag isn't really a full tag because there is no name or payload. Also, a quick note, lists of a compound tag can be especially tricky because once you read the ID and length of the list, the first thing you're going to read is the ID of any other tag, because the payload of a compound tag is just other tags. So you keep reading tags until you hit that end tag, in which you're done reading the first compound. Then you read the next compound and the next until you hit the end of the list. Here you'll see a color-coded and indented and line-split NBT file. Each number, of course, here represents a byte as you continuously read the file. And this is how you should think about an NBT file as you read it, or how a computer should think about an NBT file as it reads it. Here you'll see that same data written a little bit differently, with all the IDs replaced with what type of tag it is, and everything is given a little bit more explicitly, especially with all the text being given in actual text form rather than how they would look in bytes. And finally, here's the most simple version without all the extra information that you don't need to know. And this is the general hierarchy of an NBT file, how the compound works, how all the individual tags inside it works. Nested compounds, we've got some lists of compounds and lists of other tags as well. Officially, when you store NBT in a file, It is generally compressed with gzip. Gzip is a compression tool or library that has been around for a very long time and is proven very efficient. This gives NBT an incredibly small size, smaller than it would be even when uncompressed. However, it takes a little bit longer to read when it's compressed like that, as well as write. And so there's nothing really stopping an NBT from being uncompressed. And right now, really only Minecraft and Minecraft-related things use NBT. It's an efficient format, but it's delegated to Minecraft, and so that makes it a little bit non-standard. Minecraft will use them when storing any data. Player data is stored in NBT. All the worlds have their chunks stored in NBT. But because NBT is an ambiguous data structure that you can put anything into, it can be used in a variety of cases. Here's a file with 3D data stored in NBT, as well as a program that reads and displays it. Here's another program that takes a folder and archives it in NBT. The gzipped output file is a little bit smaller than a .tar.bz2. And that's just because there isn't as much information being put into an NBT archive. Here's also a small project I've been working on that stores all of its levels in NBT, including the textures. And while I have not delved into it personally yet, I feel like NBT would make a good candidate to send information from a client to a server, even when you're not compressing it. It's a lot less data than JSON, and it's really easy to interpret by the machines. A little while back, I started making a C++ NBT library. I've been learning about NBT for a rather long time. It's been interesting to me how such a intriguing format is used really nowhere besides Minecraft. And so if you happen to know C++ and maybe you're interested in just playing around with NBT, I've got a page linked in the description to downloading that library, how to use it, code examples, as well as some example files. There's also the NBTArchive project in the description, as well as the NBT3D project. And so, is NBT better than JSON? It depends, really. While NBT is great for typed language, small file sizes, and quick and easy reading and writing, especially when it's uncompressed, it's not really standard, and you'd have to go out of your way to learn it. Rather, I'd like to talk about NBT partially because I've spent so much time learning it and haven't really seen anyone to share this information with. It's really important to know that there are more file types than what we're given. There are always better ways to write stuff. NBT is important to know, not because you need to use it, but because you need to know that you can use it. There are more than just JSON files. There are more than PNG files. There's also QOI. There are more than MP3 files. There's also OGG files. There are a lot of different file types that aren't really used just because they're not standard, even when objectively they are better. And so, it's pretty cool, I guess. Okay, well, thank you for watching. This was kind of just a ramble video. A lot of information that I've just been holding on to that I want to put somewhere. So there it is for you. Here's a quick screenshot of different file types and like their size comparisons. You'll see that the JSON file is 10 times bigger than the NBT uncompressed file. So if that doesn't convince you that NBT is pretty much better to use in every case, then I don't know what will. The only time that JSON is smaller than NBT, if you compress the JSON and don't compress the NBT. That's literally it. But that's just how NBT works, and I'll see you in the next one.